Next example wants us to look a little bit more closely at the dot product and actually find what the dot product is. Now we've got a few key points that have been taken out of your textbook here about the dot product. The first one tells you that the dot product is what we call commutative, and that means that, commutative, which means that the order doesn't matter. So that means that you can do A dot B is the same as B dot A. The next one here tells us that a scalar, like k, can multiply across a dot product. Okay, it's a sort of distributive one. So is this one here, the fourth one. These distributive properties, the word distribute means to, to go between. Okay, so if you had lollies, and you're distributing to everyone, then you'd be giving different amounts of lollies to everyone. So the same thing happens here with the dot product across a bracket. The A distributes or goes with the B, and the dot product goes with the C as well. So you have A dot B plus A dot C. So distribute, that should be distributive. Distributive qualities that you've seen before are, for example, with multiplication. So if you had, 3 outside of x plus 1, that's distributive because the 3 distributes equally with the x and the 1. So you'd have 3x plus 3. So it happens here with the dot product, A dot B plus A dot C. The other one that you can see there, the third point down, is that A dot 0 vector equals 0. Any vector dot product with the 0 vector will be 0. There's no angle between them. Okay. This one here, this fifth one, I'm going to put actually in a different colour so you can't see it in the red. I'm going to put a big star next to that one. That's a really important property, and it's A dot B equals 0 when A is perpendicular to B. Now if we think about what that means, and please see your textbook for proofs of these properties, but I'm going to go through the proof for that one. If we think about what the A dot B is given as, so A dot B is the magnitude of A times the magnitude of B cosine theta. If A and B are perpendicular, what's the angle between them? It's 90 degrees. And what's cosine of 90 degrees? Cosine of 90 degrees is 0. So if two vectors are perpendicular and the moduluses of those vectors, A and B, are non-zero, then we know that if A dot B equals 0, then A is perpendicular to B because the angle between them is 90 degrees. The angle could also be anything if A is 0 or if B is 0, but this is assuming that the mod A and mod B are both non-zero. So that's a really, really important thing to know about the dot product. It's a really great way, and a lot of proofs look at perpendicular vectors. It's a great way of telling whether or not two vectors are perpendicular. Okay, the next one underneath there, and I'm just putting a little perpendicular here. The next one underneath here says that A dot A equals the modulus of A squared. Well, the proof for that's quite a nice one. I'll just put it next to the answer here. So A dot A would be the magnitude of A times the magnitude of A cosine theta. Now if you had a vector A over itself, what's the angle between them? Well, the angle theta would be 0. There's no angle between them. So we can actually think about this as being the magnitude of A times the magnitude of A cos 0. And we know cos of 0 is 1. So that would be the magnitude of A squared times 1, which is the magnitude of A squared. So that's where we get this result. That's also another key one. I'll highlight that one with some yellow too. Okay. This last one here is not one that you see as often, but this is when two vectors are parallel, and it's a nice little proof to yourself here to do this one. A dot B is the magnitude of A times the magnitude of B if A and B are parallel and in the same direction. So try and prove to yourself this one. Think about if they're parallel, what would the angle be between them, and if they're in the same direction. This one here tells you if A and B are in two opposite directions and parallel, that you end up with negative the modulus of A times the modulus of B. So this one here at the bottom, that's a great one. Try and prove to yourself why those two situations occur and how you actually end up with those answers. Okay, before we get onto our example, I also wanted to look at two other things. The first one is in terms of the dot product, what the dot product actually is. So we know that this is how you can find the dot product, but the dot product itself can be found without knowing the modulus and the angle. And that's if we have two vectors, A and B, and they all have different coefficients of I, A1, A2, A3, for I, J, and K. And for B, for I, J, and K, we have B1, B2, and B3. Now, when you're doing the scalar product, all you have to do is take the coefficients of I, which I'll circle in green, and multiply them together. Okay, so they're multiplied. We then add the coefficients of J multiplied together. So they've been multiplied. And then finally, we take the coefficients of K, we multiply them together, and we add them on. So all of these coefficients are multiplied together and added. Now the thing you'll notice here is this is not a vector, this is a scalar answer. So it has no I, J, or K inside it. It's only the coefficients multiplied together for I, J, and K, and then all added together. All right. What that means now is that we have a more general form for the rule than the one that we had before. So we know that A dot B equals the magnitude of A times the magnitude of B cos theta. Now, if we actually have an A dot B, which we found here, this expression here gives us cosine theta. Let's divide the left side through by magnitude of A, magnitude of B, which they've done here. And then all this formula is here is the A dot B replaced with what A dot B actually is. So the actual dot product on top of the two magnitudes. Okay, so this particular one, and to be honest, I don't tend to use that one as much as I use this one, which is A dot B over the two moduluses equals cosine theta. This is going to help you to find theta. So if you're ever wanting to find the angle theta, this is the version that you should be using. Okay. Otherwise, if you're trying to find magnitudes, you might want to use this version here.